Remember those puzzle games where you'd look through a picture book and try to find Wally? It'd be really distracting and frustrating, but after scanning through the page, voila, you'd find him tucked away in the corner with a cheeky grin. And then some other friends of yours might do the same puzzle, but instead of taking minutes to find him, they'd find him instantly. Now imagine that Wally is a glioblastoma, a type of rapidly spreading fatal brain cancer. And instead of one puzzle book, you have a stack of hundreds of patients, all of whom are depending on you for survival. We know that some doctors are better at spotting disease, but why and how? My research attempts to answer these questions, so just like any other skill, doctors can be better trained to look for disease, and yes, it could train you to be better at spotting Wally as well. But how can you possibly compare how two people view the same thing, or how one person might view two different things similarly? Well, it starts by modeling visual gaze. But how do we even begin to represent human vision with a framework? Tracking the way a person might look for Wally over a few seconds would create an incredibly complex array of data. My research suggests the answer is in an exciting combination of fractal geometry and bioinformatics, and here's how. First, let's imagine looking at a painting for a moment, and let's pretend that as your eyes look over the painting, an imaginary line is drawn from point to point as you take in the artwork. Just after a few seconds, the painting would have a lot of these imaginary lines over it, right? Well, these lines represent your visual gaze pattern, and in the first challenge my research faced was in reducing the complexity of these lines. The way we did this was with space, but not literally, it was in fractal space. Specifically, a type of space-filling curve developed by German mathematician David Hilbert in the late 19th century. This allowed me to simplify the complex gaze pattern made by the invisible lines over that painting you just imagined into a single plain list of numbers. With this list of numbers representing my new visual gaze model, I wanted to see if it could predict what someone was looking at without any other inputs. In my experiment, we did just that. I had 53 people look at two different paintings and try to predict which one they were looking at. The challenge was that there was no task, no order, and no structure. They were simply asked to look at each painting. Using a method I developed based on a bioinformatics algorithm used in protein science, I was able to match participants with the paintings they were looking at more effectively than the leading matching methods in current literature. In future work, instead of clustering participants to paintings, we can cluster high-performing radiologists with MRI scans to see how they differ from novices in the way that they look for cancers. Most of all, my research will provide an opportunity for others to use the model I've created as a framework for further behavioral research, so we could be closer to understanding the way we see things.